So let's get started. A review on assigning hybridization is if it's our thing. So wedge that structure, which you have learned in lecture and discussion. That each carbon has 4 bonds. So it should look like this. So that's a quick review, right? So each carbon is sp3 in this case. The same thing if we go to the set example for sp2, which is like this. And when you counting for sp2, so you don't have to go through all the hybridization orbitals each time. I think she also mentioned, Dr. Levens also mentioned in her lecture that the easiest way would be counting how many pi bonds you have, which we're going to do that later. So I'm just writing the example here. So both pink carbon here are sp2. And then sp, well, that's HC. So each pink carbon here is sp hybridizations. So all the blue things you are seeing here, they are possibilities, which means the more deep the color is, the more likely that you are going to find that electron is at this position. But there is going to be a space that's there are no electrons. It's almost impossible for you to find an electron in that place, and we call that one node. And the number of sigma bonds, so you should be able to know sigma bond here, sigma bond. So sigma bond is the bond like this. So there are a bunch of sigma bonds here. So number of sigma bonds you can count, right? Yes, there's a pi bond looks like this, and there are 2 pi bonds. Well, never mind. Okay, so there are 2 pi bonds in the sp hybridizations. So let's just fill in the blank. So that should be easy. This is a really quick review on that. So there are 1 sigma carbon bond and 1, 2, 3, 4, 5, 6. So there are 6 sigma carbon CH bond. So here there are 1 sigma carbon bond and 1, 2, 3, 4, 4 sigma carbon CH, 1 sigma CC, 2 sigma CH. The way that I'm writing here is the CC is the footnotes of the sigma bond, means sigma bond between 2 carbons. Okay, so pi bonds, so there are no pi bonds here, and there is a 1 pi bonds between carbon and carbon, and there are 2 pi bonds between carbon and carbon. So similarly, if you want to do like a carbonyl, then the bonds can be, you can write in the way of C pi CO. Let's back to example. Only the center carbon has the hybridization. So we are never going to ask you what's the hybridization of a terminal end, because she also mentioned that in her class that hybridization is just a theory which people use to explain things. And you are always going to respect your experimental results when your theory cannot explain them. How come CH3 is sp3? Okay, so CH3, because I meant to write like there is an R group here, sorry, but that's a good question. So the resonance structure is going to affect that. So by the time now, you should be able to draw a fermionion. Go back to where we should start with drawing resonance structure. Then that should be starting from show the lone pairs that we didn't draw for you. And then for this one, it should be very easy. That's, you do this. So if you are doing this, okay, so I leave the so the gray bonds exist as it is. The blue bonds are the bonds that's uniform. Oh, there's a positively charged because oxygen is bound to 3 things. Okay, so in this case, it's very similar to the example that she talked about in her class. So in her class, she was talking about an example of this. And then she said, if you do this to the resonance structure, then you will be able to figure out oxygen, carbon, nitrogen, they are all sp2 because resonance effect. The similar example is here. So 1, 2, 3, so they are all sp2. Well, that's okay, better. So they're all sp2 because of the resonance. Okay. So similarly, I think you should be able to do this resonance structure. So this is benzene with okay, this is actually phenol. Okay, this is a phenol. So this one, the name of this compound is phenol. So you should be able to do similar stuff. Okay. So by doing this, you can form. So I will still use zinc gray for the bonds that exist as it is, and then yeah, that's the new forming bond, and there's a positive charge. So far, is there any questions about just so the two examples that I'm listing here are very similar to the example that she was talking about in the class. So like this one. So if I'm the one who is setting the quiz, I would test you on these two, because if you know this, you should be able to guess these two as well. Do we have to assign hybridization to the R group in the first example? You don't. R just means I don't want to draw the rest of the thing. R means that it doesn't matter. Okay, so any more questions about this? I think you guys can assign the hybridization of these three by yourself. Oh, there's a question. What is the hybridization for the second example? So let me just use the same. So sp2, so here, here, here. So here. Does that answer your question? So I'm using sp2 as pink. So we are not going to test you on hydrogen because hydrogen doesn't hybrid. In her notes, she also said that, and also halogens. Okay, so let's start to assign hybridization for the example below. I think it should be easy, right? So 1, 2, 3, 4, 5, 6. All the six atoms in the first example are sp2 because they all have one pi bond. Okay, and then the second one. So first we start to see if there are any resonance structure in the second example. Did you see any? I didn't see any. So let's just assign hybridization as it is. sp3, 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 and then there's a triple bond, which is 2 pi bond actually. So it's sp. Okay, so then the last example would be, because I can see there's a resonance between the carbon, oxygen, and the nitrogen here. So all of the three that is involving in the resonance are sp2. So sp2, sp2, sp2. This is also sp2 because it has pi bond as it is, and the rest of them are sp3. sp3, sp3. So are we good with that? Why there is no resonance for the second example? So where do you think that you can resonance into? So I guess if you are asking that question, I'm assuming that you are not asking this one. I'm assuming because there are nowhere that the lone pairs can go to. I'm assuming you are asking about the ones that I was drawing. Yes, you can make this one. So that's a good starting point. But think about what is on this carbon. It's still hydrogen. So if I'm going to transfer that electron, so let's go back to the resonance. So, oh no, I cannot. So it's electron and electron here, right? If I'm going to move one of the electron here to here, but this carbon is going to, this carbon is going to blow up because it cannot accept 5 electrons. So there is already 1, 2, 3, 4. So even you just want to move this electron here, this carbon won't accept it. So but if we go to the ones that we can, so what's wrong with the oxygen? Why you can do that things here? That's if you want to transfer if you want to transfer your lone pair from oxygen here, it's because this one can move. Oh, it's because you can move the one onto oxygen. Does that answer your question? So that's actually one of the very common mistakes that people are trying to do resonance. So don't, when there is sp3, so that's a small trick that you can keep in mind. When there is sp3, that's your next carbon is only sp3 hybridized, then your electrons can go nowhere because each sp3 is happily stay as it is. Only if you can see like there's a double bond or there's an oxygen or nitrogen, which they have to be a good electron acceptor to receiving your electrons. Does that answer your question? Okay. Let me color the ones here with the exact conformation of this. So there is a blue and yellow methyl group. In the configuration that I'm drawing here, my yellow methyl group is pointing up. So it's this one. And my blue methyl group is pointing down. It's this one. So the way that I'm drawing here is I'm looking. So my eye is here. So my eye is here. I'm looking from this perspective that I can, that if I'm looking in the way as the camera is now, that my yellow methyl group is in the front and is also pointing up. Well, the carbon behind that is hidden by this, so if I'm moving, so you will be able to see this one as well. It's the one that I'm circled now in the Newman projection. So the one in front is this carbon. So the whole pink circle is the carbon at the back of the green carbon. And then there are two more hydrogens pointing up. And we are going to give this one a certain energy. So the reason that we want to do the whole practice here is, let's say if we give this one an energy, and then we are going to compare if we are rotating the second bond. So we are going to fix the first one in front and then rotate the blue hydrogen at the back. What would happen to the energy? And that's what you're supposed to know. So since we are fixing the bond in front of that, I'm actually going to do these things. So you can do that on your paper as well. So I just copy paste the one in front. So since I'm going to fix that one, right? And then see how things work. One thing more, this is anti. So anti-configuration. And the second one, when we rotate 60 degrees, where in the video, you almost cannot see the blue hydrogen or the other two. So like here, let me just do it. My CH3 is here. My hydrogen is here. The other hydrogen is here. Okay. And we call this configuration eclipse. This is the eclipse configuration. So what would happen to the energy? Because these two is gonna to knock to each other. They are too close to each other. And keep in mind, everything we talk about here is all about electrons, and electrons take the same negative charges. So it's going to generate a repulsion between the hydrogen and the carbon. So they don't want to be in this configuration. How do we describe that in our energy diagram? There's a higher energy of that, but not as high as a one that we are going to mention. Okay, since it's just the hydrogen knocking to the carbon, so you can imagine later on there's a carbon knocking to the carbon, which happens to 180 degrees, and you are expecting that one to be a higher energy. So higher energy means they're not comfortable with that. You need more energy to force them to form the configuration that they are forming now. So if we keep moving, that's 120, right? So what do you see here? So my CH3 is here, my hydrogen is here, my hydrogen is here, right? So we give this one a name gauge. So in gauge configuration, It's better than the one that we've seen before, like Eclipse, but it's not as good as the anti. Things, although this blue and this yellow is not knocking into the right position to each other, but they are closer than the anti position. So we are expecting a energy to be here that is higher than the anti position, but lower than the eclipse. So if we keep moving, what did you see here? Two metals finally is going to knock to each other. So this is another eclipse. And what happened to that? Energy. So we are expecting a very high energy. Each atom is knocking to the one in front and the back. And what makes the things worse that these are two methyl groups, which means on this yellow carbon there are three hydrogens pointing out at each other, and they're going to knock on the one that is on the blue. So that's the worst scenario, which requires the highest energy of the all configuration. And the rest of them is all symmetrical, right? So you can expecting this one to be CH3, hydrogen, right? So this is also gauge. So it's the same as before. It won't be exactly the same if this one is not, if the blue one is not a methyl, but you will do this exercise in your practice on discussion menu. So you will see that. So this is methyl group if we keep moving, right? And this is hydrogen. And this is hydrogen. Okay, so this one is eclipsed. So you are expecting, and then finally, we go back to 360. Everything is the same with before. That's the anti position. So you are expecting to know the relationship between gauge, eclipse, anti-position. You are supposed to write any of the formats if we ask you, and you should supposed to using a smooth line to connect between all those points and know there is a circle for the whole rotation. So there's a question. I don't understand how the molecule is moving. So the molecule is not moving. The molecule is just rotate. Because if you check your notes on hybridization in lecture, she actually mentioned that sigma bonds can rotate, pi bonds cannot rotate without breaking it. So here, things these are all sigma bonds. So sigma bonds can free rotate as it is. So that's one of the reasons that we want you to know their wedge dash. So come back to our discussion one. That's this blue is dash in, and then these two are wedge out. So that's why it matches. So there's another question. So how do you know the energy for each type? This is the first example you learn. If I just go to my discussion menu, see, that's everything we expect you to know. So we told you it looks like that. And the examples that you are going to see in your discussion menu is going to be very similar to that. So they actually ask you a even simple one, which is just 2 hydrogen. So can you see the similar things? And in the discussion menu, in the ones that they ask you to do, because these 2 hydrogens are the same, instead of the ones that we're talking about, that's 2 carbon. So you're expecting the 3 eclipsed to be the same energy. So that's why it's the same. So you just need to know the relationship. Okay. So why is the yellow methane in the front of the Newman project? Because I said the way it is. You can also do the other way around, which you need to change the blue thing in the front. Yes, you can. It just depends on from which perspective that you are observing everything. But the thing you should keep in mind is once you are selecting one carbon, like I decide to look from this perspective, then you should keep consistent until you finish the whole 330 degrees. Okay, So there's another question. So does gauge always have a lower energy than the eclipse? Most likely, yes. Topic of discussion here is actually hybridizations. Okay, so what's the angle between the sp3? So you should know that right now by now. So what's the shape? So tetrahedral, right? So look at the molecule. So the two carbons are one behind each other, rotated until the hydrogen in front. Blah blah blah. Okay, so the centimeters. The point of the second question is, will this rotation affect, just read the question, affect the distance in carbon 1 and carbon 2? So here, because it's only two carbons, so the blue and the blue and the yellow are hydrogen, okay? However you rotate, their distance between the two carbons is not going to change. Does that make sense? So you won't change. I don't know what's the distance in your model. Mine is 5 centimeters. So you can put whatever number you want here. Let's just put 5. Okay. So rotates the real carbon 60, and then using a ruler measure how far from the hydrogen on C1 and C2 in your model. So that's the exercise that we were just doing. You are expecting to know that when it's gouged, this two hydrogen has a longer distance than when it's eclipsed, where they're on top of each other. The ones here, eclipsed conformer, are higher in energy than staggered. So staggered is the one that looks like this. Okay, then the staggered. The staggered is the one that's every bond is in 60 degrees to each other. Electron repulsion, yeah. So electron repulsion occurs when electrons in aligned CH bonds. So this, and then we did the drawing just now together, right? So that's the exercise that you can do on your own. So using the model butane, so when we use in the model butane, that's the blue and the yellow are carbon. So the ones that, think about the ones that we're using. So look at the molecules. So let's just ignore those measurements of the distance between those two and answer some of the important questions. So gauge conformers are higher in energy than anti-explain. It's because when you go to the gauge, in gauge rotamers, that the larger group are close to each other, which is the blue and the yellow. They are close to each other than anti, where they're in the opposite direction to each other. So they ask you to draw another one, which is fine. You can practice on that. And then for SP2, it's more like, it's kind of a concept question that you should know. So what's the angle between CH? So you should be able to know that it's 120 now. And what's the molecular shape around the carbon? So it's trigonal plane. So this one is actually a little bit important because trigonal planar take one of the bonds off. So the real trigonal planar means they're on the same plate, which is they're on, I'm trying to push it really hard. So they're on the same plate. So each of them should be 120 degrees to each other, each bond. Since there are two sides, if I want to attack something onto the black carbon here, you can go from top or it can go from back because it's a planar. While if it's tetrahedral, there's something else pointing up here. It won't be as easy as you to attack from the back than from the front of the black carbon. So does that make sense? So that's why we want you guys to know there's a difference between tetrahedral and trigonal planar. If it's planar, it's totally on the same plane, which is it's a paper plane on the whole three things. You can attack something to the black carbon on both sides. Just keep this one in mind, because very soon in chapter 6, you're going to learn mechanism, which is SN1. That this one actually matters very much. Let me put, so that's why. So we're just talking about trigonal planar, and I just stress this ahead. That's why this is important. So attempt to rotate the carbon-carbon bond. So imagine there are two carbon-carbon bonds, and you cannot. Well, the reason you cannot is because it's a pi bond, and pi bonds cannot rotate. So the same thing, and that would be very easy for the rest of them because If you cannot rotate, you cannot draw a diagram on SP2 with Newman projection. What is cis and what is trans? So you won't use it until 118b, but it's fine that if we're going to talk about. So CH3, hydrogen. So if the bulky group, which means this doesn't have to be a CH3, but if the group has a higher priority than the hydrogen, so we're just talking about these two. So if the two groups that has higher priority is not on the same side, a line here. If they are on the same side, it's Z configuration and equals to cis. If they are not on the same side, and equals to E. So when to use Z, when to use E, it's we're going to talk about that in one stage discussion. That's where nomenclature. So otherwise, it's still some concept ones. So which isomers do you think is more stable and why? So the trans, the one here, is more stable because the cis isomer has increased steric hindrance. Steric hindrance is a good way to describe when you have two bulky groups and they're knocking to each other. When they doesn't want to be so close to each other, you say there's an increased steric hindrance. Do you think trans 2-butenes and cis 2-butenes will interconvey like Ant and Gauch rotation conformer? Why? No, because they cannot rotate. So it's still about breaking the pi bond. They won't. So you are never going to draw energy diagram like that in SP2, like what you have been drawing in SP3. Do you think trans 2-butene and cis 2-butene will have the same physical properties? Of course, no. And you're going to learn how different it is in 118b. So you don't have to know what exactly the difference is now. SP, okay, so what's the angle between CHHC? So that's easy, 180 degree. So what's the molecule shape? So it should be linear. A time to rotate alkyne around carbon-carbon bond. No, you cannot, because there are two pi bonds. Even you just have one, you're not going to rotate. And then build the model of, okay, let's say 4 carbon of that, 2 butane, and sketch the structure. So would you expect butane to have alternative rotation? No, because it's going to look the same. So it's still going to be the same. So there's no difference. So we ignore all the measurements because that's going to be different on each model. So that's basically the end of the discussion. And then we'll see you in 5 minutes in office hour. Okay, bye-bye, everyone.